Hello and welcome to this podcast for Electropages. I'm your host, Robin Mitchell. Today we're talking to NXP to get down and dirty with AI in the edge. Now, just before we get into this conversation, I've got my first question for you, which is could you please tell the audience who you are, what you do, and what you like to do in your free time?
Right, Robin, thanks for having us. I'm Ali Ors. I lead the strategy and technologies for everything that's AI in our processor portfolio. NXP is one of the premier embedded processor vendors that includes microcontrollers, like traditional microcontrollers, advanced microcontrollers, and applications processors. So anything from what would run in your thermostat, in your toaster, to industrial robots and vehicles and cars. So a very wide portfolio of application domains, and we service a lot of processing technologies for those domains. Now, more and more of that has a lot of AI content, so we're putting a lot of enablement in both hardware and software to make that happen.
Fantastic. And so one thing that I'm seeing a lot in the industry at the moment is that everyone's trying to put AI onto smaller devices, whether it's microcontrollers, sort of SoCs, or sort of system on modules. As a company, what would you say has been the biggest challenge that you've faced when it comes to actually getting these solutions onto tiny, small devices?
I mean, there's many. One of the biggest ones is, of course, a lot of these AI technologies are created on much larger and more, let's say, capable or resource-rich environments. We're talking about cloud servers, large server farms, etc. So when you're creating something in an area that has a lot of abundance of both compute capability, of memory availability, of data availability, of connectivity, and then you come down to trying to fit it, as I said, from toasters to industrial robots. These are all restricted domains. You're trying to achieve certain power envelopes, like trying to maintain your power, your heat dissipation under certain amounts. And so that shift from I have all the resources I need, I'm going to build a beautiful AI solution, to now I need to run this on something that's practical and near the node of where it's going to be used. Sometimes there's a big step function that needs to happen to fit that big technology into where it is practical and interfacing with daily life, with human interaction and use. So that big step is where we're seeing a lot of difficulties and challenges, or friction points, let's say, and we're trying to solve constantly for removing as much as possible those friction points.
So to try and give myself a better idea in terms of the size of these AI models, because one area I tend to play around a lot with is things like large language models and stuff. So that you're talking up to 13 billion kind of parameters, 8 bits. So you're talking maybe 8 to 12 gigabytes of RAM used to sort of run and store that model, even locally. But when it comes to using AI on smaller devices like microcontrollers, like embedded processors, what kind of sizes are we talking about? Because I'm trying to gauge in terms of like the memory usage.
So maybe we'll make a distinction on, let's say, generative AI or transformer models and generative AI, like the chatbots or the chat GPT like things, or LLMs, large language models, and how those play, because those are still fairly large. Yeah. The well-performing ones now are in the hundreds of billions of parameters, if not trillions. The ones that get most of the news cycle and the hype around them, of what OpenAI has released, of what Meta has released, what Google releases into the ether. When you try to get this into edge devices, even on larger edge devices, you get into where you have the main processor itself. So you have a compute amount of compute available to you, but you also have DDR, so your memory, your dynamic RAM memory. And these are typically in embedded systems like 8 gigabytes or 16 gigabytes type of amounts of memory. And so the model and a rule of thumb that still applies is about for every billion parameters, you need a gigabyte of RAM memory, both for storage and exchange room. So practically, if you only have 8 gigabytes of DDR memory available to you, you're not going to be able to fit something that's larger than 7 or 8 billion parameters onto that end device, end node. So maybe if you had 16 gigabytes, you're looking at 15 billion parameter models. The nice thing is that this trickle-down effect that happens in a technology gets released, and quickly there's innovation to try to make it more efficient in both area and functionality. We're seeing a trend where today the smaller models that are like optimized for edge deployment almost match the performance of a much larger model of the previous generation, and this previous to next generation cycle is accelerating in availability, in time frame. So you're able to run something that's quite capable in a very small form factor on the edge. So you're able to run 7 billion parameter models that give you maybe the previous generation's 30 billion or 70 billion parameter model performance. And you're getting good results. And you also have to remember that as you're deploying these things on the edge, you're not going to have a conversation about the French Revolution with your thermostat.
No.
Like if you're trying to put a large language model into that and you're trying to have a human-machine interface that leverages the LLM's capability of understanding conversational language better, you're not going to be, having these very general world politics type of discussions or a very wide discussion that you might have with your laptop and a chatbot on your laptop, etc. You're going to be asking about changing the temperature. What is the weather today? How do I set it? I feel hot. Can you and let it make those decisions for you? So the domain that it needs to understand is more restricted, and you can leverage that to optimize the models to run on more edge friendly ways in these devices that are embedded devices. So and very effectively.
And it's interesting you mentioned about the thing with the generation, because I've seen that myself, where, like you say, a 1 billion model parameter a year ago would not be very capable. Now it can almost match on par with models that are significantly bigger than it. And so, and again, I'm guessing this is sort of like a training situation whereby as more data becomes available, we refine the training, we get it better, we prune what we don't need, we make the model smaller, more efficient, use less energy, and therefore can use less parameters. So it's not so much a case of the fact that newer technologies are necessarily coming out to make AIs, suddenly much easier to run. It's also a case of the industry has had time to adjust their models, time to train their models, time to reduce the models to understand how to fit them better to the constraints they have for those embedded systems.
Correct. So, I mean, there's multiple vectors of optimization that's happening. The models do change. So, or the smaller variants of the models are different. They're more their compute is more optimized. I mean, you hinted at part of the challenge is, when you're training, you want a lot of rich data representation in your data. So typically, training is done with floating point representation, 32-bit, maybe 16-bit even, but it is usually floating point so that you maintain accuracy and a rich data representation. But to be efficient and optimal when you get into embedded platforms, the trend is usually to try to get your compute into integer format, to represent it in integer, which is more efficient in your compute logic that's being used, so that the amount of area that you have for your compute becomes more efficient, that the calculations are simpler, but that comes at a cost of losing accuracy. Yeah. So your data representation goes from something that's very rich and can reflect a very wide range of numbers to something more restricted. And that quantization step, that's what's called quantization, going from a larger data representation into a smaller format. So that quantization and the result of the loss of precision has to be recovered. So, and this existed pre-generative AI and LLMs, etc. I mean, it existed with convolutional neural networks. It existed prior to that in even computer vision, like with just traditional computer vision in pixel representation formats. But once you get into integer, your computer is more efficient. The way you store your data is more efficient. So if you can recover that accuracy loss that you sustain via additional training or some clever methods around it, then you have a very large improvement in your efficiency in your runtime, and that becomes quite critical to making these things run on embedded platforms.
So when it comes to an embedded platform versus, say, a mainstream device you might use in your home or a data center, one sort of big difference I've noticed is when you run an AI model on something like a CPU versus a GPU. And the speed difference between the two is insane. You can't really run things on a CPU if it's a large language model. But if you're going to an embedded device, I know that there are sort of like accelerators that are coming out, but most of the time these types of hardware accelerators don't exist. So what I'm kind of curious about is, how do engineers cope when all they have is a sort of a standard compute module, a typical CPU, and don't have the accelerators needed to get those models to run faster?
So to the benefit of the CPU, I mean, CPUs are it's like the jack of all trades.
Yeah.
They can run anything, and that's their superpower in a sense. So you can throw any problem at it. It might not be efficient, it might not be optimal, but it will run. So that, going back to some of those friction problems that we talked about in trying to get from larger devices onto embedded devices, CPUs don't have that general, oh, it just can't run it. It'll just be maybe slower. It's not as efficient, but it can usually run everything that you're trying to do. And so you can actually, so a lot of development ends up being on the CPU, getting it just to run. So you get results. You might be getting, less optimal inferences per second or token rates, but eventually then you start porting over onto architectures that are more performant or have higher performance for these types of calculations. That could be GPUs. On embedded systems and NXP, especially at NXP, what we're doing is we're building out accelerator architectures ourselves. So we have our own accelerator architecture called EIQ Neutron NPU. It's a neural processing unit, when we first bring in a model, it'll usually just port onto the CPU, and we'll see a certain token rate. So that token rate might be for a 3 billion parameter LLM or a 7 billion parameter language model. That might be like 3-5 tokens per second, which is not a very good rate of token generation, especially when you're talking about how humans read at over, for it to be a good user experience, you want over 6 tokens per second generation on a readout, or if it's spoken back. So if you have a text-to-speech action happening and you're hearing the audio, you want it to be above 8 tokens per second, so that you're not getting choppy audio, you're not getting a choppy experience when you're reading a terminal that's reflecting on you. So you're always trying to get above that 8 tokens per second, and anything beyond that becomes even better. And we saw that when we started off on the CPUs, it might be just borderline 6 to 7 tokens per second. But as we moved a lot of the computations onto the accelerator, you're getting into the 9 tokens, 10 tokens, and above, which is where you want to be from a sweet spot perspective of you're generating tokens at a good rate from a user experience perspective, but you're also not burning a lot of power and dissipating power or heat, trying to over-engineer the design.
So in a previous podcast, when we talked to ARM, one question I had for them was about the challenges of trying to build accelerators in an industry where AI models and the method of computation keeps changing. And I think one sort of great example of this would be like Hugging Face and the introduction of transformers versus the convolutional models. So the moment that change happened, it's kind of like accelerators which were built around one type of AI suddenly can no longer be used on the new type. So I suppose my question to you is, at NXP, is that something that you've particularly had issues with, or is that something that kind of grinds your gears when you're trying to develop a new accelerator and someone's come up with a brand new mechanism for running the AIs?
Yeah, I mean, it's a perpetual problem, right? Like you said, I mean, there's always something new coming, especially in the AI field. It's so dynamic that there's always something new coming in from the research environment saying, hey, suddenly we went from, and this change rate is also accelerated, which makes it even more difficult. I go back because I do have a background in building for vision specifically. So we went from traditional computer vision and suddenly convolutional neural networks broke out, and your compute was different. So the accelerators that we were building for traditional computer vision acceleration had some applicability, but they weren't highly optimal. And you see that in the cycles of between the efficiency that you get on a first generation accelerator with something that's brand new versus suddenly the big jump in efficiency that you get as the second generation of these accelerators come out that are better oriented towards the problem at hand. And then something new comes in. So ChatGPT and transformer models and generative AI comes in, and suddenly your CNN accelerator, your maybe second, third generation CNN accelerator that has now become very, very effective and efficient, is no longer as efficient on these new models. So you're trying to balance as well. We don't build accelerators. I mean, our overall portfolio is meant for general compute.
Yeah.
Anyway, so it is a heterogeneous compute environment. So we have CPUs, GPUs, NPUs for the acceleration, even DSPs that could be for audio and different various applications. So you do have multiple types of cores in NXP's i.MX lineup, for example, of application processors that can handle these. And then it becomes a software problem of until you get to a more purpose-built accelerator, how do you solve today with the hardware that you have for the software problem that's new, that's being thrown at you? And with that in mind, we do try to leave some level of flexibility in our design. So not everything, so we don't go in and design for a specific, let's say, AI model or like a CNN AI model. If you solved for only a specific model or a small set of models and said, I expect my customers only to be using these, or my developers only to be using these, then you would have a very big problem when things shift. And it's a very dynamic and shifting ground domain. So we leave the flexibility in the acceleration, so that allows us to actually adapt as new technologies come out. And that's why, it's tough to say it's luck, because there's a lot of engineering that goes into it. I don't want to take away from the R&D teams. They're actually putting in a lot of effort into balancing that flexibility and efficiency and optimization of the hardware. So we're able to run generative AI models today on hardware that we built without generative AI in mind. And that, getting those above 10 tokens per second rates is on hardware that was built for CNNs predominantly. So very good performance on CNNs, but achieving the needed performance on token rate generation with generative AI.
And again, I know you say it's not fair to call it luck, because your engineers are working absolutely hard to get these things to work. But the thing is, again, like you say, the AI industry is so volatile in many ways that maybe another model type does come out, and suddenly your customers need a new type of accelerator, which is not available on any other platform at that point. So it sounds like to me that what you guys are trying to sort of focus on is creating like a family of, or a range of products with various accelerators in various configurations, so that you've always got the ability to choose the exact device that you need for your application.
I say, the portfolio approach is one of NXP's greatest strengths. Like I mentioned, it's a very wide portfolio with a wide capability aspect. But for AI, a lot of the effort goes into the software enablement. So, the hardware is, by the time the device is available, the hardware is locked. You can't do much. But we've gone with designing our own proprietary accelerator core, the EIQ Neutron NPU, because we anticipated and knew that we had to deal with a lot of software churn and a lot of software enablement to handle these changes that are happening outside of us. We're part of the ecosystem, but it's also that ecosystem moves. We're not controlling the way it moves. We're one of the players in that. So that ability to influence the software, ability to build software to create a gasket, or to create an adaptation layer to the world that's changing very fast, and a hardware that's, by the time it's available, is locked until you get into the next generation. That could be a 2, 3, 4-year cycle by the time you get into designing a piece of hardware that's adapted to today's available models and technology.
So when it comes to AI in embedded situations and in embedded applications, what would you say are like the top application types for those AIs? Are they LLMs? Are they vision? Are they kind of like predictive maintenance? What do you typically see?
That's a very loaded question, especially just coming from being at NXP. It's a very loaded question. We have a big presence in of course, automotive, so vehicles, transportation type of technologies. We're a big semiconductor and processor vendor in that domain, but we also have a big play in industrial and IoT. IoT being more like the consumer side of our business. So in each of those, let's say, large verticals, you have multiple smaller verticals in all of them, and NXP does play in all of these domains. And when you look at automotive, let's take automotive for example. You have AI technologies around the autonomous driving and driver assistance systems, the ADAS systems. Those could be vision, radar, LiDAR, or sensor fusion type of feeds. You have AI getting into electrification, like your battery management systems of keeping the cells healthy, but also charging and discharging, and using AI to make diagnostics on these battery systems, or be tracking their health. Then you get into inside the cabin. Again, you have vision and audio-based AI technologies, both checking for monitoring the driver, monitoring occupancy. In the infotainment and e-cockpit, you start getting into LLMs for natural conversational HMI to control devices, or to enhance the audio experience that people are having. So a lot of different AI models and use cases are available in each of these segments. And then on industrial, like you said, it could be, I mean, we've built on both ends of the spectrum. We build enablement for what's called time series. So usually anything that is not vision-based or camera-based, could be sensors, signaling coming in from vibration, temperature, voltage, current, any of these things. And then that's used for understanding maybe predictive maintenance, like going towards predictive maintenance, understanding the diagnostics and the health of the overall system. This could be the health of the motor. This could be the health of the compressors or various robotic systems or machinery that's happening. So you have time series based models running there, and usually time series is a smaller model itself, just from a size perspective. But then in an industrial setting, you could also have a lot of vision based AI models running to detect manufacturing faults, very high frame rate, very high resolution imagery to detect if something is being manufactured to the standard that it needs to be, if there's anomalies in that. And you can again have LLMs to do conversational HMI with the machine operator and the machinery itself. So you could have, and we're building enablement of what we call the Gen AI flow, where you could have a front end speech recognition, or event recognition. So somebody, imagine a big piece of machinery and somebody walks up to a terminal, it automatically recognizes that this person is an authorized operator of this machine, has been trained on this machine, can actually query it. And then that operator maybe asks, either types in a question asking for diagnostics from the last 24 hours, 48 hours, or is querying right then and there the machine's health situation or operational statistics. Or they can do this via audio. So there could be a speech recognition, which is another AI model running. Then that speech recognition feeds into an LLM that understands the question coming in, saying, give me a report of the last 24 hours, and if anything's wrong. And that then might be spoken back out with a text-to-speech model, which is again another AI model, or could be pushed out to a terminal. All of this actually can be automated, that you don't even have that operator walking up to the machinery. You're actually constantly monitoring it. And if the machine senses that something's off, the parameters, it can actually call the operator to come to it. So then you get into these AI agents and agentic AI flows of automating a lot of things that we see as regular flow of operations. You're getting into a lot more autonomy in the AI systems, and them making decisions and calling out additional services and additional agents to interact with the overall system. So it's an ever expanding domain. And then on IoT and consumer, again, very similar use cases. Like I said, you could be interacting with your thermostat, your security service, or system in the home. You could have various applications that are running. Your coffee machine even has AI in detecting how do you like your coffee, or how is it going to best make coffee based on the hardness of the water in your home.
I tell you what, it sort of I might be wrong here, but the impression I get from this sort of introduction of LLMs and text-to-speech modules and the way that we interface with these machines is akin to the transition from the terminal and the keyboard to the GUI in a typical computer, whereby people didn't have to type commands in, they could start clicking and pointing. And when that happened, it had a massive, massive impact on the computing industry and the way that people use computers. Would you say that you think that kind of agent AI type of machine, which essentially sits between humans and the fundamental piece of hardware they're trying to interface, do you think that might be the next step to human-machine interfacing?
I fully believe that, yes, and it's not just at the consumer level, so not just us in our homes. It's also at the industrial level and in various aspects, where one of the biggest traction points that we're seeing for this technology is what I keep referring as natural conversational HMI. And that applies to a lot of different devices. And there's a lot of technology that sits around that in making that practical. And it doesn't need the 70 billion or trillion parameter model running on the edge device, because usually each device, your thermostat only cares about what its domain is. Your coffee machine cares about its domain. A much more complex factory automated manufacturing flow will have its own domain of, I'm making widgets and that's what I care about. And, this is how you make it well. And this is when it's anomalous or there's something wrong with the system. So these things are contained. So the models are smaller, but the benefit is in, you and I might have different accents. We go up to the machine and it still understands what we're saying. We might have different colloquialisms. We might have different ways of interacting. And it also allows for the training of these operators and the ramp up to be much faster potentially. So you're not only assisting in the day-to-day operation, but you're also assisting in, getting more efficiency out of your human workforce as well.
And I'm guessing the reason for that is because the AI can apply intelligence to an order or a request. So if you take a human operator and you've got a piece of machinery and you say you've got to know how to let's say it's a CNC. And you've got to reset it to 00. You've got to check the health of the motors, blah, blah, blah. Normally, you have to go into a terminal or the software application, find the key values, look at the graphs, blah, blah, blah. If you have an AI and go, can you set this to 00 and then check the health for me? It just understands how to translate that into all those sort of effectively boring and meaningless little tasks and functions that it needs to perform, and then provides back the report. And like you say, you could then say, can you show me what it was like for the past 12 hours? Now, that LLM has never been trained on here's how to get 12 hours of data. But because of the way that it's been trained, it sort of knows how to interpret that information, go, here's the past data that I think I found in the past 12 hours. And so it helps to sort of simplify and eliminate the need for a large number of lines of code to try and figure out every single function you'd ever wanted to do.
Yeah, exactly. It's kind of creating that. It generalizes that knowledge, so that deep knowledge is not required anymore from everybody operating on that machine. So you're kind of creating this. You're leveling the playing field, or actually creating a certain amount of intelligence that the human operators can rely on, that's running on the machine, and you don't need to have that on the human side, or have a very experienced operator interacting with the device.
And I think if you think about the way that people think as well, we are generalized machines as well. So if someone says to me to find some setting on a CNC, I have not been shown or told how to do that, but I sort of know from experience that, well, I suppose if I go into options, and I go into sensors, I suspect I will find something there, and then the AI is essentially replicating that step, saying, well, I know about options, I go to options, whatever. So I think, like you say, it's, in terms of the human-machine interface, it's almost like a human-human-machine interface, because it's just trying to add another human layer that's, or a digital human in this case. It's just sort of doing that back end for you.
Yeah, I mean, it's really about taking that information and making it available more readily. Because I mean, usually that information is available somewhere in a user's manual.
Yeah.
Somewhere in a technical bulletin, it's there. And then you have techniques of feeding that into the device. I mean, we use it. There's a technique called retrieval augmented generation, or RAG for short, for example. And you can use that to give context to a model like an LLM model without changing the fundamentals of the model. That kind of ties into.
Well, that's a great example. That's a great example, because one thing I can give my own example for NXP right now, which is any large embedded microcontroller or microprocessor like an NXP part, the datasheet, thousands of pages long, you know. And if I want to set a register or a bit in a register, it's hard to get through the datasheet. But now you can pass it through an AI and go, which register do I need to do to turn on the UART port? And it'll go, boom, here you go. Now, an engineer could do that themselves, but it would take them a very long time, and it's a wasted effort, because all that really mattered in that situation was that I turn on the UART port. And so, like you say, RAG service, which I think a fantastic addition to any AI system, they just help people find the information that they need faster and more efficiently.
Yeah, that database of facts, of context, is available to the LLM to query, to leverage in its responses, and you're getting exact things. So another part of LLMs, when you're not using techniques like RAG, and you're trying to put them onto embedded systems that we've had to solve for and kind of remove that other friction point, was, okay, well, you take an LLM, most users, unlike CNNs, where a lot of users were coming in saying, oh, I saw this research paper, I saw this CNN, it kind of does what I want it to do, but I'm going to make my own, I'm going to customize it. That becomes a lot more difficult in LLMs, just because the amount of compute and data needed to create these models and then train these models is, let's say, cost prohibitive. I mean, it needs both compute resources, it needs the right technical expertise and human resources, and then it needs the data as well. And these are all very intensive in terms of expenses.
Well, I've done that myself. This is why most people, anyone who wants to train in AI, you usually just fine tune a base model, because the amount of energy you need is insignificant compared to what it took to actually train the base model in the first place. So, and I'm guessing what would happen in that situation is that if you want to train your own CMM, what you'd really do is take a base model, apply your own data, fine tune it, and then reapply that model in the field.
But I mean, my point is that on CNNs, like if you really were adamant about creating your own, the hurdle, the limits of entering that weren't so large. Now with LLMs, it's much harder.
Yeah.
Just from a cost perspective. So there's a lot more entropy towards using off-the-shelf state-of-the-art and then trying to fine-tune it. But even fine-tuning state-of-the-art LLMs is quite costly if you're getting into any fine-tuning step that requires a level of retraining and data generation. So techniques like RAG that we've built into our flows allow you to take that state-of-the-art. You're not modifying the main model, which has other implications around regulatory bodies as well. So you can say, hey, I haven't touched the original model. All I've done is I've created this database of context for it to leverage and be more exact in the use case and the applications that I'm deploying it into, which is critical in the domains that we.
That is a really good point. Just to quickly pick up, on the point you made about the not changing the base model because of regulatory issues. It's like if it's an automotive system, for example, and you've got an LLM that's or just an AI in general that's finally been AEC2. What is it? AEC
ASIL.
200.
Are you talking about the ASIL?
No, the one you use for components when it's AC something qualified. 200.
ACQ 100 is around usually.
So like those parts which are ACQ qualified. If you have a model that's been qualified and you start messing around with it, it loses that qualification, like you say. So the RAG, like you mentioned, on top of that, just means that you don't affect that fundamental underlying thing. But what I am kind of curious about, and I want to ask you this question, which is the sort of like, in terms of the future of AI. And AI agents on embedded systems and what NXP is doing, what would you say are the biggest challenges that you suspect that you're going to face coming in the next few years?
I mean, I look at it as this. I mean, the technology is moving very fast. We're adapting. We're building hardware. We're building software as we're trying to bridge to the efficient hardware around it. I think security is going to be a big challenge. So making sure that these systems are secure, and that goes back to I mean, NXP has a very big, let's say, presence and emphasis around security and safety, just from the domains that we're in, industrial and automotive. But we give a lot of focus and effort in making sure that our devices are secure. There's ways of securely provisioning them as they're being deployed, and we're keeping the security in place. And with agents and agentic AI, we're getting into situations where these agents, if they're not being designed properly, you could get into situations where they create additional vectors of attack and additional vulnerabilities around the systems. So it has to be built in a way that you have the fundamental device security. Also, when we talk about embedded systems now, unlike systems in the cloud where you have a centralized location for your vulnerability, now with edge deployments, you're everywhere. So you run the additional risk of physical access to the devices. So you need to secure your device very well. So your fundamentals of security need to be in place. And then as you scale into agentic flows and AI agents, you need to maintain that security both at that edge device and its connectivity and the way it's running its protocols. Like, I mean, there's protocols like the Model Context Protocol with MCP that Anthropic released and made available that is heavily used. It's almost like the authorization level is an optional piece right now. So that needs to be built into everything you're doing. You need to have that as a part of the build out, so that you're not creating vulnerabilities as we're deploying these systems.
And I guess that things like prompt hacking and prompt engineering, like they do in LLMs already, can still be a threat to these smaller models. Where, you know, if given the correct kind of prompt, like override this or ignore this or do that, you just might be able to get around it, as you were mentioning before about the alternative attack vectors. Mm-hmm. So how? Sorry, go on. Sorry.
No, please.
So I was only going to ask, so in an embedded system, how would you defend against something like that?
So the way you're building out your authorization schemes in embedded systems, I mean, the fundamentals remain the same. So it's restricting access, and keeping things to limited authorization, so that anything that's agentic is only accessing absolutely what it needs to do its own task. So you're sandboxing or creating protections. There is no there are terms here on the security side. So you're only giving it authorization for absolutely what it needs to have authorization to. And you're maintaining a certain separation and obfuscation of some of the code, so that it's not openly available. Yeah. I mean, we've had stories out in the press of, you know, certain things being out in plain text, you know, logins and authorization codes and authorization tokens.
Or the more famous one, or the more famous one, GitHub, when someone pushes their code base and suddenly an API key is sitting in the open.
Exactly, and you got to also protect against prompt injections. You have to have measures to prevent potential malicious actors from manipulating the inputs to an AI agent to then cause either unintended actions or to cause actions that provide access to something that they were not supposed to have access to.
Brilliant. So just before we wrap up this podcast, I've got one more question for you. For the audience who are watching this video, if they want to get involved with NXP Solutions and are looking to do the next generations of AI on embedded systems, what would you recommend that they do?
Definitely visit nxp.com/AI. So that's like our landing page around everything that's AI. Our tools are open, so you just need a nxp.com account, which you can get with either your personal email or your organizational email. So all of that is open, and you can get access to all our tools that allow you to build solutions, and you can even eventually access the hardware. These are because they're embedded, they're meant for more cost restrictive deployment. So the hardware kits are quite reasonable in price as well. And you can get started very quickly on building systems that could deploy into anything out there that you interact with daily. And the software is widely available. We have tools that are at even different levels of expertise. So you can build like a time series solution that checks if your motor has an airflow clog, for example, just with an AutoML tool that we call the EIQ Time Series Studio. So you just provide the data, and it'll actually create models for you. You can deploy and test them, or you can build your own models with the EIQ toolkit. So that allows you to fully create from scratch an AI model, or like we were talking about, port a state-of-the-art to your own use, retrain it, deploy it onto the systems. And if you're more interested in building out for generative AI and these agentic AIs, we have the Gen AI flow tooling that gives you that whole flow of, hey, I need a speech recognition in the front end of it. I need to provide it context with a RAG optimization. I need to have text-to-speech for the system to talk back to me through audio. All of these are like Lego blocks of building. So our main focus is to remove anything that we see as a friction point for our developers. And if that's lack of data science knowledge, we have AutoML flows. If that's lack of optimization to get a large LLM down into an embedded platform, that's tools like Gen AI Flow. If you want to get more sophisticated and build your own, you have the tools for that as well. And really, all of that is sitting on top of the hardware layer that has the needed acceleration to really run this efficiently on the edge.
Fantastic. Thank you ever so much for taking the time to see us today.